Hello, and welcome back to the course on Physics for Engineers. So before we proceed with this lesson, let us first have a review of the previous topics. So in kinematics of motion, you discussed about one-dimensional motion with constant acceleration, and you were given four kinematic equations. So this is one of the kinematic equations. This is the other one. And the last two are for determining the final velocities. The first two equations are for determining the final positions, and the final two are for determining the final velocities. But of course, you can solve any variables that is in that equation. So these are the four linear kinematic equations. So for this lesson, we will be discussing about the rotational analog of those equations. So we will now discuss rotation with constant angular acceleration. So in rotation with constant angular acceleration, or constant alpha, the angular kinematic equations is basically or not exactly, but basically the same as the linear kinematic equations. You just change the x, the variable, the position variable, which is x, y, or z, into theta. You change the velocity v to omega, the angular velocity, and you change the acceleration a into alpha, the angular acceleration. But basically, they're all the same. They're basically the same. So these are the four angular kinematic equations. So we actually have derived two of these equations in our previous we discussed the examples of the previous lesson. So we have derived this one, the one equation for the final angular velocity. It's just in terms of the initial angular velocity plus alpha times t. So alpha here are the alphas here, the angular accelerations here are assumed to be constant. So they're constant, so meaning they don't change. They don't change with time. So maybe this is not exactly how the previous lessons presented these four angular kinematic equations, but it's basically just the same. I just, for instance here, this should be theta minus theta naught here. I just place the theta naught inside here, and here this should be square here, so I just took the square root. Okay. So the term theta minus theta naught again is the angular displacement. So you can actually just replace this with delta theta, or the angular displacement. So we will use these four equations to our specific problems. Okay, let's now go directly to examples. Okay, so this is the exact problem that we had in the previous lesson. But in that lesson, we were still not presented with the angular kinematic equations. But now, we already know the angular kinematic equations, so we can just directly use them. Okay. So for letter A, so you are given an initial angular velocity of 1.50 radians per second, and you are given the angular acceleration of 0.300 radians per second squared. Again, that means the angular velocity will increase by 0.300 radians per second every second. And what is the angular velocity after 2.50 seconds? Okay, so you have four angular kinematic equations to choose from. Equation 1, 2, 3, 4. We are given with the initial angular velocity, omega naught. We are given with alpha, so 0.300. This is our alpha. And we are given the time, is equal to 2.5 seconds. And the unknown here is the final angular velocity. So it is obvious that we will use equation 3, because given ang angular velocity, given ang alpha, given ang time, we can now solve for omega. So actually, this is the equation that we have used in the previous example. So you will have omega is equal to omega naught plus alpha t. You substitute all those values because we already have solved this before. I will no longer do this again. And you will get an answer of 2.25 radians per second. Okay, how about the second problem? Through what angle has the wheel turned between 0 seconds and 5 seconds? So actually, in the previous problem, we have derived another equation for that. It's actually this equation, equation number 2, where, if you will remember, this is the average angular velocity. Another term for, another equation for average, which is just you add, if you want to average, say, n numbers, you add all of those n numbers divided by n. So if you have two numbers or two values and you want to take the average and add those two divided by 2. If you have three values, then add those three values, divide by 3. That's the concept of averaging. No need to elaborate on that form. Okay, so we already used this equation actually, and it works. It gave us an answer. Now, I want to try to use another equation, say equation number 1. So, for the second problem, you already know the final angular velocity. You have already solved it, 2.25 radians per second. You already know the initial angular velocity that's given. You're also given the time. How about the initial angular velocity? So usually the initial parts, if it's not specified, you can always assume that to be 0. If it's not specified, you can always assume. But again, if it is specified, then you need to use that value. But if it's not specified, then you can always assume it to be 0. So your equation becomes like this. Oh, sorry, I forgot. We don't need to know the initial angular velocity for this case, because, sorry, initial angular position. We don't need to use the initial angular position because what we are trying to find is the angular displacement. So I'm just gonna transpose this to the other side of the equation, such that is this. The other side of the equation becomes theta minus theta naught. And theta minus theta naught is the angular displacement, which is what we want to find. Okay, sorry, I'm gonna use pala equation number 1. So that one. Transpose that one there, and you get theta minus theta naught. So you will get the angular displacement is equal to omega naught t plus 1/2 alpha t squared. So all of these values are actually given. Omega naught is 1.5 radians per second. The time is 2.50 radians per second. So you will get a final unit of radians here for this product. Plus 1/2 alpha is 0.300. Time is 2.50 seconds squared. The final unit here is also radians. So you will get the same result. You will get 4.6875 radians as in the previous lesson, and this is still equivalent to 268.57 degrees. Now, what is the difference, or what is the advantage by using either of the two equations, equation 1 or equation 2? In the previous lesson, we used this equation 2. We derived this equation 2. But here, in this example, the same problem, we use equation 1, but we have obtained the same result. But what are the advantages and or disadvantages? Now, if you use equation 2 on this problem, there's nothing wrong. But there's a disadvantage. What if you fail to get the correct answer for omega? Because that is the first problem. Find the final angular velocity after 2.5 seconds. So if you the disadvantage of equation 2 is if you got the wrong answer for omega. Even though you used the correct solution, but since you obtained the wrong, you used a wrong, say, value, or you calculated a wrong value for omega, then your final answer will be wrong. So that's a disadvantage of using equation 2. While for equation 1, if you use equation 1, you will notice that you are only using given quantities. Omega naught is given, time is given, alpha is also given, angular acceleration is given. So this is the safer choice. Equation 1 is a safer choice as compared to equation 2. But again, if you're sure with your calculations, either of the two equations can be used. So let's now have another example. So in this example, it's a DVD. I don't know if you still know what is a DVD. This is now an obsolete technology. So you have just finished watching a movie on DVD, assuming you still have a DVD player, and the disc slowing down to a stop. The angular velocity of the disc at time is equal to 0. So meaning you are timing here. So you have a stopwatch, then you start at time is equal to 0. You measure that the angular velocity. So this is now the initial angular velocity is 27.5 radians per second. And its angular acceleration is constant at, so you will notice that it's negative here. But there are also problems that they will not mention the negative value. They will just, but you will just assume that it's negative because the disk is slowing down. So meaning it's deceleration. So the acceleration is negative. So negative 10 radians per second squared. So what does this mean? This means that the value of the angular velocity will be reduced by 10 radians per second every second. So a line PQ on the surface of the disk. So this, you draw a line PQ at the surface of the disk, and at time is equal to 0, the line PQ is aligned at the positive x-axis. Okay. First question, what is the disk's angular velocity after 2 seconds? So actually, you can just use manual calculation here for letter A. You know that the initial angular velocity is 27.5. It's the velocity at the start. And the acceleration is negative 10 radians per second squared. Meaning, every 1 second, the velocity will decrease by 10. So from 27.5, after 1 second, it will now become 17.5. It will be reduced by 10. 27 minus 5 minus 10, it becomes 17.5. And after another second, 17.5 minus 10, then you will get 7.5. So 7.5 radians per second squared. So that's the answer actually for letter A. But we will try to use the formal way, using the angular kinematic equations. Okay. So we are trying to solve for the final angular velocities. We are given the initial angular velocity, we are given the acceleration, we are given the time. So we use equation number 3 for letter A. So for letter A, we have omega is equal, the final angular velocity is initial plus the angular acceleration times time. You substitute these values, you will have 27.5 radians per second plus the angular acceleration is negative 10 radians per second squared. I'm no longer going to write the unit, times time, which is 2 seconds. So the final unit here is radians per second. Since you're engineers, I encourage solutions like this. It's not necessary you will put the actual unit of the quantities, as long as you put the final unit of that product. So this is radians per second squared. This is second. So radians per second squared times second, you get radians per second. You can only do this if you are using standard units, SI units. So that one. So this is negative 10 times 2, negative 20. So 27.5 minus 20, you get 7.5 radians per second. So this is now the velocity after 2 seconds. Okay. Second question. what angle does the line PQ make with the positive x-axis at this time? So after 2 seconds, what is now the angle of the line PQ, this line, this red line here, with respect to the positive x-axis? So we are looking for the final angular position. So in this case, since our line PQ is along the positive x-axis, so therefore this angle theta naught is 0 degrees. So theta naught is 0 degrees. So we are now trying to find the final angular position. So what equation will we use? Can we use the first equation? Can we use the second equation? Oh, it's pretty much the same as the first problem. So we can use the first equation, this one. We can also use the second equation, and again, this is disadvantageous because omega here is a calculated value. It's not a given value. Well, in equation 1, if you use equation 1, all of the values that you will get are given values. So this is all now 0, since our initial angle is 0. The final angle, so for letter B, the final angle theta will just be omega naught t plus 1/2 alpha t squared. So you substitute all of those values, and you will get 1. So omega naught is 27.5 radians per second. Time is 2 seconds. So the final unit here will be radians. Plus 1/2 alpha is -10. Time is 2 seconds squared. So this is radians. The final unit is radians. So you calculate this one. So you will have 27.5 times 2 plus 1/2, then 2 squared is 4. So you will get 35 radians. So you need to convert this into degrees. So you need to multiply the conversion factor from radians to degrees, which is just 2 pi radians is equivalent to 360 degrees. So if you multiply that one, 35 by 360 divided by 2 pi, you will get 2005.35 degrees. Now, what does this mean? 1005.35 degrees. It just means that it has undergone many revolutions after 2 seconds. So, in order to appreciate or to get the equivalent of this, we need to divide this by 360. 2005.35 divided by 360. So basically, this is 5.57 revolutions. So that one, this is actually equivalent to 5.57 revolutions. So we know that one revolution is 360 degrees. So we only need, since we are already only after the angle, the line that the angle makes with the line PQ. So we only need to get what is the equivalent of that 0.57 revolutions. So 0.57 revolutions in terms of degrees. So one revolution is 360 degrees, so you just multiply it. 360 times 0.57, so that is 205.2 degrees. So the angle actually here is 205.2 degrees. So 2005.35 degrees is just equivalent to 205.2 degrees. Because, again, one whole rotation is 360. If you have another rotation, the total, that angle now is 360 times 2, but it's still the same as 360, still the same as 0. So the angle now is 205.2 degrees. So this angle is in quadrant number 3. So most likely your line PQ will now be somewhere here, and with an angle of 205.2 degrees. So that's the angle that the line PQ makes with the positive x-axis at this time. So originally from this position, it will undergo 5 revolutions, and then 0.57 revolutions. So this is the angle that we want, the 0.57 revolutions. Okay. So let's have another example. So the rotating blade of a blender turns with constant angular acceleration of 1.50 radians per second squared. So this means that every 1 second, the angular velocity will increase by 1.50 radians per second. So how much time does it take to reach an angular velocity of 36 radians per second starting from rest? Okay, you can actually do this again the manual way. So starting from rest, you will have 0 radians per second. After 1 second, it will now become 1.5. After another 1 second, another 1.5, so it will become 3. It will become 4.5. It will become 6, and so on until you get 36 radians per second. And you count how many seconds is that. So that's actually no longer practical in this case, unlike in the previous example. So in this case, we need to use the formula, the angular kinematics equation. So we are given with the acceleration, 1.50 radians per second. We are given with the initial angular velocity, starting from rest. Starting from rest means 0 radians per second. And we are also given the final angular velocity, omega. And we are asked for t, time. So we can use equation number 3. Actually, that is the only equation that we can use. We can use equation 1, 2, or 4. Only equation 3. So in equation 3, omega is given the final angular velocity 36 radians per second. This is 0. This is given 1.50 radians per second squared, and so we can now solve for time. So since this is 0, omega naught is 0, then the angular velocity, the final angular velocity, is just alpha times. Okay, so that's for letter A. So to solve for time, divide by alpha, so you have omega over alpha. So you will have 36 radians per second over 1.50 radians per second squared. So the final unit here will be seconds, because this is time. So 36 divided by 1.50, and you will get 24 seconds. So if you do this manually, it will take you 24 manual counts before you can reach the final answer. And that's not a very elegant solution. So this is the elegant solution. So 24 seconds. It takes 24 seconds from 0 or from rest to reach a final angular velocity of 36 radians per second if your angular acceleration is 1.50 radians per second squared. Now for letter B, through how many revolutions does the blade turn in this time interval? So in the interval of 24 seconds, how many revolutions does the blade turn? So how many revolutions does the blade turn means we need to find the change in angular position, or the displacement, angular displacement. So what equation will we can we use? We already know the time. We are trying to find the angular displacement. So there are 3 actually. We can actually use equation 1. So just transpose this to the other side of the equation, so that you will get theta minus theta naught. So you already know the initial angular velocity, the time, the acceleration, so you can use equation 1. Can you use equation 2? Yes, because you already solved omega. Again, this would be disadvantageous because omega is a calculated, the calculated value here is time. So anywhere that has time here will be disadvantageous. So meaning the most advantageous equation. So actually you can use equation 1, 2, or 4. You can use equation 3 because there's no theta here. There's no angular displacement in this equation. So you can use 1, 2, and 4. But since equation 1 and 2 contains time, which is a calculated value for letter A, what if you got the wrong answer for time during your calculation? You plug in the wrong values. So that will be disadvantageous. You will get the wrong answer. So equation 1, 2, and 4 can solve letter B. Any of these three equations, you will get the same answer. But the safest equation is equation number 4. Because from equation number 4, alpha is given, omega naught is given, omega is also given, and you are trying to find the change in angular position or the angular displacement delta theta. So what we will do is we will just square this from the original. That's actually the original kinematic equation. Omega squared is equal to omega naught is 0, so no need to include that. So the square root now disappears because we square it. So you will get 2 alpha, and that's change in theta. So that is now the result for using equation number 4. So we solved for the angular displacement. So this is just omega squared over 2 alpha. So you will get the final angular velocity, which is given 36 radians per second. Square that, divided by 2 times alpha, which is 1.50 radians per second squared. And the final unit should be radians. So you will have 36 squared divided by 2 times 1.5. You will get 432 radians. The problem states ask for the unit of called revolution. So you need to convert this into revolution. So we have 2 pi radians. That is 1 revolution. So divide by 2 pi. So if you divide your answer by 2 pi, you will get a value of delta theta, or the angular displacement, of 68.75 revolutions. So in 24 seconds, starting from rest, it rotated for about 68, almost 69. So 68 and 3/4, 68 and 3/4 revolutions. And that's the time that it got to an angular velocity of 36 radians per second. Okay. Okay, so that is the last example. So basically, the rotation with constant acceleration is very similar to the one-dimensional motion with constant acceleration. So just change the x, the positions, to angle thetas. Okay, so for the next lesson, we will be talking about the last lesson for angular kinematics. We will now try to relate the linear kinematic quantities and the angular kinematic quantities. So what's the relation between v, the linear velocity, and omega, the angular velocity, for instance? So I will see you in the next lesson.